Hello guys, good evening. Can you hear me?
Yes, sir.
What we did last class? I think we did with Werners Coordination Theory, right?
Yes, sir. We wrote drawbacks of Werners theory. That was the last thing.
Okay. So primary, secondary valency we have discussed. We also discussed the number of ionizable ions. Okay. So right. So we have few drawbacks in Werners Coordination Theory. That's why we require another kind of theory for bonding in coordination compound, right? And then we got valence bond theory. This valence bond theory is very much similar that we have done in chemical bonding, if you remember. Okay, all those hybridization and all, we'll discuss it here. So the next theory is valence bond theory. 1 second, just to give me. Okay, so Werners coordination theory, just one question we'll see, and then we'll move on to the next theory in coordination compound, that is valence bond theory. Okay, so look at this question.
You're on mute.
Yes, so formula and moles of AgCl precipitate per mole of the compound with excess AgNO3, right? So formula is given here. The first one is PdCl2 dot 4NH3 NiCl2 dot 6H2O PtCl4 dot 2HCl COCl3 dot 4NH3 PtCl2 dot 2NH3. These are the molecules given. need to the primary and secondary valency and what is the formula of this molecule, because there's nothing like, it is not written in a square bracket or something like that. So how many ligands are present in the complex part that you need to find out, plus the primary and secondary valency for all these compounds you need to find out. If the number of moles of AgCl precipitated for per moles of this is 2 for the first one, then 2, then 0, then 1, and then 0. This is the data given. Find out. Primary valency, secondary valency, and the formula. Done? One second, guys. Okay, so the first one, yeah. You see the number of moles of AgCl precipitate, right? So AgCl that precipitate, it depends upon the number of ionizable chlorine atom there, right? So moles of AgCl precipitate is 2. It means there are 2 chlorine atom which is present outside the complex, the coordination complex, right? Hence the formula for the first one, if you write down, the formula should be this. Palladium is the metal, NH3, 4, and then Cl2 outside. Okay. So from here, if you find out the primary valency, what is the primary valency here? The primary valency is 2, the oxidation state, and secondary valency is 4, that is the coordination number. Okay, number of ionizable chlorine atom is 2. Second one, if you see, we have 2 AgCl precipitated. Again, it means this 2 chlorine atom presents outside the complex, and hence the possible formula is this according to the given data, dot Cl2, okay, not dot, Cl2, okay, Cl2. So from here again, the primary valency is 2, and secondary valency again is the coordination number 6. Okay, so the third one, you see, there is no precipitation here. It means all the molecules ions are present inside the complex. So we'll have Pt. So basically we can write this as H2PtCl6. This way also you can write H2PtCl6. So primary valency here is the oxidation number. So primary valency is this is again we don't know condition. So HCl is there. What should be the primary valency here and secondary valency? Secondary valency to 6 we are getting. What is the primary valency here?
+4.
I think we should write it down this way. The correct representation here is this. No, correct representation here is this. Just a second. The third one, chlorine is the donor from HCl. So we can write down this as PtCl4 dot 2HCl like this. Right? There's no charge on this complex. That's why the primary valency is 0 here. Secondary valency is 6.
The HCl itself is Van de Graaff.
Chlorine is the donor atom there. Lone pair of chlorine.
Okay. So I want it ionized.
It is there in the complex. See,
okay, yes, sir.
we are writing down this formula based on this data. If it is outside, if I write no H2, then it will ionize also.
Why, sir?
Right. Sorry?
It will be H2PtCl6 then. No. There won't be any
H2PtCl6. Yes, H2PtCl6 if you write, that won't satisfy the value which is given over here. Right. It says 0 AgCl. See, actually, primary valency is also we consider the number of ionizable chlorine atom. Because of that only we'll have the charge on the complex.
Yes, sir.
Right. if you have like this, you see Cl2 present outside. You see the primary valency is the number of chlorine which is present outside the complex here. Here, all chlorine will write down inside, right? But oxidation state, if you check this, you can also write down this way. I am not writing down the primary valency with respect to the oxidation state here, because if you write down this one H2PtCl6, then the charge on platinum you are getting as +2, -2, -6, so +4 you are getting over here, right?
Yes, sir.
But +4 is not the primary valency. Actually, what happens? This out of 6 Cl, 4 Cl satisfies here the primary valency of this, right? But this AgCl that precipitate here, this is only possible when the chlorine is present outside the complex, right?
Yes, sir.
And we also know the primary valency is nothing but the ionizable,
Chlorine atom.
chlorine atom or any other atom which is present, right? So here you see here ionization is possible, H plus and this PtCl6 2 minus we get. Okay, ionization is there, but chlorine does not comes out like this. So like this you can write, but this is the most appropriate way to represent the molecular formula of this, since this satisfies that there is no precipitation, there is no ionization in this complex, we can say. Here still we have ionization. That's why this way you can write, but in some book they have written this way also. As far as AgCl precipitation is concerned, this also holds true because this chlorine won't go out into the solution. This chlorine also won't go out into the solution. So both way you can represent, but primary valency here, since there is no ionization of chlorine atom, we are considering this to be 0.
Sir, but the primary valency isn't dependent on the number. Oh, okay. Sorry. Oh, sir, I actually made a mistake. Sorry.
Okay. Fourth one, you try fourth one. What is the primary valency you are getting in fourth one? Only one atom should be outside, right? So 4 NH3 or 1 Cl should be inside, right? So 5, is the secondary valency, and the primary valency would be?
Sir, 3.
So 1.
I'll write down fourth one. Wait.
Yeah,
See this.
please.
Yes, correct. So since one chlorine atom gets precipitate, so formula should be CONH3 4 Cl2 and Cl. This is the possible formula we can write because the only one precipitation is there. Okay, so it's primary valency. We have 3 Cl. No, secondary valency is 6. 4 plus 2 6. Primary valency is what? Only one chlorine atom that goes out, okay? And -2 will have here. Primary valency would be 3.
Sir, so in the previous one, why can't we say that the primary valency is 4?
One second, I'll check that. I think PtNH3 twice and Cl2. In this case, what we are getting primary valency as 0, obviously 0 here. Yeah, there's 0 here. And secondary valency as 4. Only secondary valency. Here we have primary valency 1. You get here primary valency 1. This is fine. See, actually, one thing you must take care here. This 2 chlorine atom which is present inside, this satisfies both valency, right? Primary as well as secondary, right? So secondary valency, if I've written 6, right? So this we are already considering here. So we won't consider these 2 chlorine atom if we write the primary valency here. The same thing I'm doing here only. So one thing, the difference here is what? usually if you see the last Werners coordination theory we have discussed, that primary valency corresponds to the oxidation state of the metal. So if you find out the oxidation state, we are getting it as +3. But primary valency in this compound is the valency which considers the negative ion, which satisfies only primary valency. Secondary valency, we are not considering here. So in this 2 chlorine atom, it satisfies both primary as well as secondary. So while calculating the primary valency, we'll count only those atoms which are present outside the complex. Okay, so here also you see, if you write down this way or this way, obviously there is no chlorine present outside the complex, hence primary valency is 2. Right, primary valency is 2. Primary valency is 2. Here there is nothing outside, no chlorine outside, primary valency is 0. Right? This chlorine, why we are not considering primary valency? Again, I am repeating, because this satisfies both primary as well as secondary. So here, on the basis of this data, we consider only those ions which satisfies only primary valency, that is 1. Yes?
The last class you gave that same 4th example and you told primary valency is 3.
Yes,
Structure
we're talking about this compound, 4th one?
Yes, so the 4th
Yes.
one. Yeah.
So the question is what? Question is the primary valency. So primary valency we consider only, see, it's basically the language that is written. Okay. Because if you look at the Werners coordination theory, the primary valencies corresponds to the oxidation state of the metal. So what is the oxidation state of cobalt here? It is +3, right? Is it?
Yes,
According to this, the primary valency should be 3, but that is the maximum value. Out of 3, 2 chlorine atom satisfies the secondary valency also. That we are considering here in 6. That's why in this case, based on the data given, we only consider those chlorine atom here in this case, which is present outside the complex. According to that, only we'll write down the primary valency. Why this we are not considering? Because this contributes into the secondary valency as well. That's why we are not considering this, only this one we are considering.
Okay.
Okay. So this kind of questions, easy questions you will get, you will easily understand that what is the possible structure of the molecule in Werners coordination theory. So one kind of question is this, another kind of question, they can give you the formula and they can ask you the primary valency or secondary valency is given, they can ask you the number of ionizable chlorine atom. Okay, like suppose in this one, because there are many different kinds of question possible. In this one, you see, if they give you this formula and says the primary valence, the secondary valency is 4 for this one, secondary valency is 4. What is the number of ionizable, what is the number of ions we get in the solution? This kind of questions they can frame. Okay. This is another type. They can also ask you how many, moles of AgCl precipitate when this molecule with secondary valency 4 reacts with AgNO3. This kind of question means other way, here and there they can change the question. This kind of question they can ask. On the basis of the molecular formula, they can also ask you the order of molar conductivity. Again, that depends upon the number of ions. Any of these kind of questions possible here in Werners coordination theory. Other than this, there's no possibility of getting any other kind of questions. Right? This is the first bonding theory, which obviously fails. Reason and the drawback I have given you already in the last class. So to overcome this, we've got the new theory, another theory of bonding that we call it as valence bond theory. Valence bond theory, again, we have postulates, and then based on that postulates, we can find out the bonding of coordination compound. All these things we are going to. It's a very important topic. This one is write down the another theory of bonding of coordination complex, that is valence bond theory, VBT in short. Write down this theory mainly deals with deals with the geometry and the magnetic property of the complex. And the magnetic property of the complex. Okay. The main postulates are the first point, write down the main postulates, the first point. The central metal atom, CMA, the central metal atom loses a definite number of electrons to form ion. A central metal atom loses a definite number of electrons to form ion. This is the valency of the metal. Okay. Again, I am repeating. The central metal atom loses a required number of electrons to form ions, definite number of electrons to form ions. This number is the valency of the metal. Next one, depending on the coordination number, the central metal atom, and when I say central metal atom, write down CMA. Okay. Depending upon the coordination number, the CMA has equal number of vacant. The CMA has equal number of vacant sp and d orbitals these orbitals forms the CMA has equal number of vacant spd orbitals. These orbitals forms hybrid orbitals together, right? And that thing is same, like the number of atomic orbital combines, equal number of hybrid orbital forms. Okay, that is same. So it is very much similar to the, I'll repeat. Similar to the valence bond theory in the simple compound. Okay, depending on the coordination number, the central metal atom has equal number of vacant sp and d orbitals. These orbitals forms hybrid orbitals together. Okay, this is same till here. Now the difference here is, the third point, the difference is, in case of strong ligand, there may be some rearrangement of electrons in the atomic orbitals against the Hund's rule. Right? One thing here, I said in case of strong ligand. Okay, so what is a strong and weak ligand? We haven't discussed yet. Okay, this will understand when we do CFT, that is crystal field theory. Okay, there I will tell you how to find out. Basically, you have to memorize that which ligand is strong and weak, and not that difficult. If you solve some questions, you will memorize it easily. But for this one, I'll let you know that this particular ligand is weak ligand or a strong ligand. Okay. So this is the rearrangement against the Hund's rule, right? Next, fourth one. The ligand and the metal bonds and metal bonded with coordinate bond which has considerable amount of polarity. Considerable amount of polarity. Right? Means the bond is polar. Now the last point here is the same thing. If there is unpaired electron, if the complex contains unpaired electron, then it is paramagnetic, otherwise diamagnetic. Diamagnetic, if all electrons are paired. So third point is the new thing we have here. Otherwise, you know all other things easy, right? Depending upon the coordination number, we can have the understanding of hybridization of the complex, and hence we can understand the geometry of the complex also. So this table, all of you have drawn. All of you have written this.
Yes, sir.
Okay. So this table you draw. One side we have coordination number, Cn stands for coordination number, and then we have geometry, and then we have hybridization. Coordination number could be 2, 3, 4, 5, 6. Geometry is just a second. I'll have some space here. 4 and then 5 and then 6. If it is 2, then the geometry is linear. Hybridization is SP. If it is 3, then it is trigonal planar. Hybridization is SP2. If it is 3, then two different geometries are possible according to the hybridization. If it is tetrahedral, hybridization is SP3. If it is a square planar, is DSP2. For coordination number 5, two different geometries are possible: trigonal bipyramidal or square pyramidal. And the hybridization is, we can have either DSP3 or SP3D. Keep this in mind. It is not like trigonal bipyramidal is DSP3 and square pyramidal is SP3D. It could be anything. Okay. Here we have this thing. Tetrahedral SP3, square planar is DSP2. If it is 6, then we can have a square octahedral or square bipyramidal. Both are the same thing only. Octahedral or square bipyramidal. Square bipyramidal. And the hybridization is D2SP3 or SP3D2. Yes. Am I audible?
Yes, sir.
Okay. No. See, guys, whether the geometry is TBP or square pyramidal, it depends upon the molecule. Okay, it has nothing to do with the geometry, do with the hybridization here. Okay, don't consider this as TBP is DSP3 or square pyramidal is SP3D. Okay, it's not like that. One more thing here. This D2SP3 and SP3D2 is what? See here, if you write down D2SP3, means in this, how this hybrid orbital forms. This hybrid orbital forms by the combination of two 3D orbital plus one 4s orbital and three 4p orbital. Right? These are the numbers we have. SP, DSP3. Okay. So one 3D, two 3D, one 4s, and three 4p. So here you see we have 4s, 4p orbital, and along with this we have two inner shell orbitals. 3D orbital is there, 4D is not there. So there is inner shell orbitals present here when you write down D2sp3. D2sp3 hybrid orbital forms when 3D combines with 4s and 4p. So this is inner shell orbitals, hence we call it as low spin complex. This kind of orbital, it forms low spin complex because inner shell orbital is involved into this low spin complex. But on the other hand, if you write down D2sp3, sorry, sp3d2, this means we have 4s plus 4p plus 4d. Right, this kind of combination is there. It means it is high spin complex. Okay, this is the term we use, high spin complex. Just a second, Ayush, just a second. Okay, one more thing, low spin complex is generally forms, like low spin complex generally forms with a strong ligand. In case of strong ligand, low spin complex generally forms. High spin complex forms when we have weak ligand. What is a strong and weak ligand? We'll discuss that. Okay, just to write it down here, we'll see that. What is a strong ligand and what is weak ligand. Okay. Okay, just a second, I'll go back. Yes. Copy this. Wait, Aditya, just a second, wait. Low spin means when lower d orbital involves, then it is low spin complex. Just the term we use. When the inner shell d orbital involved, it is low spin complex. When outer shell 4s, 4p, 4d involves, it is high spin complex. Done? Okay. So these are the postulates of valence bond theory. Based on this, we can find out the geometry plus the magnetic nature, right? Whether the molecule is paramagnetic, diamagnetic, if it is paramagnetic, then how many unpaired electrons, all those informations we can get. One by one, we'll see. One more very important thing is here. All these discussion that we are doing, out of all these, the coordination number 6 is the most important one. Coordination number 6 is the most important one. Mostly they ask question from this only, coordination number 6. Okay, but we'll discuss all the coordination number like 4, 5, and 6 we'll discuss. So first of all, examples we write down here. Example we are taking for coordination number 4. First one. See this question. The question is, we have NiCl4, 2 negative, is found to be paramagnetic. Is found to be paramagnetic. Explain hybridization and geometry. Hybridization and geometry. Okay. Now, for your information, all halide ions are weak ligand. Okay. Halide ions are weak ligand, that you should know. X minus are weak ligand, must remember this. And generally, strong ligands are those in which the carbon is the donor atom. If carbon is the donor atom, then the ligand are said to be strong ligand in general. These two things you must keep in mind, but once you solve some questions, you'll understand that which ligand is strong and which ligand is weak. Got it? Fine. So how do we do this question, you see? First of all, what you do, you find out the oxidation state of the metal, which is here +2. So nickel has how many electrons? 28. If you draw the electronic configuration, argon 4s2, 3d8. Okay. For Ni2 plus, because the metal ion is Ni2 plus, so this would be argon with 3d8. So if I draw the orbital diagram here, this is 3d, for example. This is 4s, and this is 4p. 1, 2, 3, 4, and 5. So 3d has 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. And and this is 4s, 4s, and this is 4p. And 4d is not required. 4d is this side, not required, because coordination number is 4 only. We required only 4 orbitals here, so that we can get 4 hybrid orbitals in which the ligands, 4 ligands can donate its lone pair. Right. So what happens? This 4 orbitals, empty orbitals, goes under hybridization before the bonding, and it forms 4 sp3 hybridized hybrid orbitals, in which the 4 chlorine atom donates its electron pair, right? The ligand donates its electron pair and makes a coordinate bond with the metal, right? Obviously, if you look at this, the hybridization is sp3, geometry is tetrahedral, right? There are 2 unpaired electrons, and hence the molecule is paramagnetic, which is also given in the question. Yes, Cl minus is a weak ligand, so there is no pairing against the Hans rule. Should note down this. Correct. Now, suppose if this is a strong ligand, like Cl obviously is a weak ligand, then there is no pairing against the Hans rule. If it is strong, then this electron pair, this jumps over here and makes this orbital vacant in that case. Then this orbital also will take part in the reaction, and 1, 2, and 2 orbitals will take from this from this p subshell. Then the configuration will be, or the hybridization would be dsp2 in that case, square planar geometry. Okay, this depends upon the nature of the ligand that you should know, whether the ligand is weak or strong. Keep these 2 terms in mind. Okay, this helps you a lot in solving this kind of questions. Now, you see the second question here. We have a molecule, say NiCO4, carbonyl group, is diamagnetic. Explain hybridization and geometry. Try this one. Tell me the answer. CO, the carbonyl group CO, yes, DsP2 square planar. Okay, CO is a strong field ligand that you should know, right? Carbonyl group is a strong field ligand. So there will be pairing against the Hans root, right? There's no zero oxidation state of nickel is zero here. Hence, Ni is argon 4s2 3d8. Okay, so this is 3d orbital. Then it is 4s 4p. Since it is coordination number 4, we require only 4 vacant orbitals. 3d 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and 4s will have 2. Right, 4s will have 2. Then what happens, you see? Okay, all of you are getting DsP2. There will be pairing against the unsud. So this 2 electron, it jumps here into the inner orbital of 3d, makes this 4s orbital vacant. Okay, so after this rearrangement, the orbital diagram is this. We have 2 electrons in each of these orbitals. This is vacant, 4s and 4p. So this goes under hybridization and it forms again sp3 hybridized orbital. This is sp3 hybridized orbital. So hybridization for this complex is sp3. All electrons paired, so it is diamagnetic. Diamagnetic. Geometry is tetrahedral. Right? This is what the answer is. How did you get DsP2? Oxidation state is 0, no? Yes. So oxidation state is 0. Try this one. NiCN4. And cyanide is also a strong ligand. NiCN4, 2 minus is the complex. Find its magnetic property, geometry, and hybridization. Is it DSP2 you are getting? Yeah, it is DSP2. It's not SP3. Yes, because here the oxidation state is +2. So whatever you have done in the previous case, that is applicable here, right? So this would be, if I write down the electronic configuration of Ni2 plus, it is argon 4s0 and 3d8. The orbital diagram is this. One, two, three, 4, and 5. 8, 0 electrons, 0 electrons. Now, since this CN is strong ligand, then there would be pairing against the Huns rule, and this electron which is unpaired, it jumps back into this orbital and makes the electron paired, and hence this orbital becomes empty here. So here, after this rearrangement, the orbital diagram looks like this: 1, 2, 3, 4. Each of these orbitals will have 2 electron. One orbital is vacant, 4s, and it is 4p. So it is 3d, 4s, and 4p. So 3d orbital, 4s, and 4p, 2 orbital here. So this goes under hybridization, and it forms 1, 2, 3, 4 DSP2 hybridized hybrid orbital. So hybridization is DSP2. Geometry is square planar. Magnetic properties is diamagnetic. Okay, these three things we can understand, okay, from this thing. Now, if I ask you one more question, they ask in this particular kind of geometry, that which d orbital is involved in this geometry, because we know we have 5 d orbitals, we have dxy, dyz, dzx, dxy, y square, and dz square, right? So out of this 5, which d orbitals is involved in this geometry? Could you answer this?
Can you repeat?
Sorry?
So can you repeat once again?
I said we have 5 d orbitals, right? In 3D subshell, we have 5 d orbitals. Out of the 5, which d orbitals involves in this geometry? Because only one d orbital is involved, no? Only one d is there. So which d orbital it is out of the 5? Okay. See, you have to first of all, 3D is a subshell, guys. Okay, Adhar, Aditya, 3D is a subshell. I'm talking about the orbital. So within 3D, we'll have 5 orbitals. Like for 3D, it should be 3D xy, 3D yz, 3D zx, 3D x square y square, 3D z square. Okay. So which d orbital is this one? Okay. 5th one. Acha. Why it is dx square y square? Dhyan. Just guessing. Okay, fine. By the way, your answer is correct. The answer is dx square y square. There is no, defined logic for this. That this is why this is happening. Okay, this is factual actually. But I'll discuss one small thing here. Probably with that you can understand that which d orbital is involved, right? Obviously, it is not a given method in the book. But yes, from this particular thing, if you do not know, if you forget in the exam, then you can think like this, you will get the answer. Okay, what d orbital or which d orbital is involved? No, it does matter. It does matter because the orbital has its own orientation around the nucleus. That's why it does matter. See, actually what happens, square planar geometry is what? with geometry you can understand. It is not that difficult also. All of you will get it. The square planar geometry is something like this. Once again. Yeah. The square planar geometry is this, correct? Suppose this is the square planar geometry we have. And metal is present somewhere here in the center of the square. And how do we get the square planar geometry? When the ligands are attached at these corners, yes or no? So to ligands to get attached with this metal at these corners of the square, it has to approach the metal from these directions. I'll show you what direction it is. What I was about. So if the metal has to form, if the ligand has to form D, square planar complex, then this must have to approach the metal in from these directions, along these lines we can say, or along these directions. It must have to approach this way. So suppose all the 4 ligands are coming from this direction and it is trying to approach the metal for the bonding. It is trying to donate its electron to the metal from these directions. All these directions the ligands are coming. Correct? So obviously the orbital, and this metal has all the d orbitals. Correct? All the d orbitals. So obviously the orbitals which are present along these lines, that particular orbital will have the maximum probability to involve in bonding. Yes or no? Are you getting me? The angle, or the like the line through along which the ligand is approaching the metal, along that particular line, whatever orbital is present, if it is, right, if it is, whatever orbital is present, that particular orbital will have the maximum probability to involve in the bonding, because the ligand is approaching towards that particular orbital. Now you see the another thing, if you consider this line, obviously the square diagonal, it bisects at 90 degree, right? This is the 90 degree. So what I am trying to say here, that I can assume that this axis is, suppose this I am assuming as x-axis, and this I am assuming as y-axis. Why? Because the angle is 90 degree. And perpendicular to this one, suppose we have a z-axis, which is not required here in this case, but is required in the other cases, right? So obviously we know this dx square y square orbitals are along this axis. They are the axial orbital. It is present along this axis. Which orbital is this? Dx square y square, is it? All these things I have discussed in chemical bonding already, right? So this orbital is what? This orbital is dx square y square. That's why in this square planar complex, the orbital that is involved is dx square y square, because the ligand is approaching head on to this orbital. Did you get this?
Yes, sir.
Right?
Yes, sir.
Now, what is square bipyramidal? We have these 4 ligands, and along with these 4 ligands, we have 2 more. One is from this side, and other one is from this side. Yes or no? That is only square bipyramidal. So if I ask you which d orbitals are involved in square planar geometry, square bipyramidal geometry, what is your answer?
X square, y square, and z square.
Dx square, y square, and dz square. Yes, very good. So with this kind of the pictorial diagram that we have discussed, you can have the idea that which orbital is involved in a given geometry. Okay, d orbital. There are many times these questions in NEET exam. Even in JEE also they have asked this question. Okay, so write down this this thing that we have discussed here, the geometry here and the d orbitals involved. Geometry and d orbital. So if the geometry is square planar, the d orbital is dx square y square. If the geometry is square octahedral or square bipyramidal, the orbitals are dx square y square and dz square. If it is square pyramidal, it is only dx square y square. If it is TBP, trigonal bipyramidal, it is only dz square. This is the orbital d orbitals involved in the geometry.
Sir,
Yeah, tell me.
sir, so can we say that the pz orbital is left out in the 4p orbitals?
In which one? The
Out
other.
of the 4p orbitals, out of the 4p orbitals, pz will be left out, sir.
PZ, no, we cannot say whether it is PZ or PX or PY. Okay. Mostly PZ, we don't consider because PZ normally forms sigma bond first. That's why we always assume internuclear axis along the Z axis, right? But yes, they won't ask you which orbital is left behind in P subshell, whether it is PX, PY, PZ, because that is not in our control. You cannot, say that theoretically.
Okay, sir.
Understood? Yes. So this is also important. So coordination number 4 we have discussed. Now you see coordination number 5. Same kind of thing you have to do. Nothing, difference here. But yes, we'll do 1 or 2 examples so that you can understand it. It's important also. So we have a question molecule that is FeCO5. FeCO5. Okay. And the information with this is FeCO5 is found to have zero dipole moment. Mu net is 0 for this. Zero dipole moment. Find its hybridization and geometry. Try this one.
Sir, what is that coordination number is equal to 5 on top
Coordination number is 5.
of Fe, sir?
Yes, this is the complex. Coordination number is always defined for metal.
Yes, sir.
So what's the charge of the complex?
Nothing. 0. No, the dipole moment won't affect hybridization. But yes, with dipole moment, see, you try this Aditya once, okay? You will understand why this dipole moment thing is given. Okay, try once to do it.
Okay, sir.
What is the geometry, Srishti? Square bipyramidal. CO is a strong ligand, correct? Yes. What is the geometry, Pratham, you're getting? Okay, see this. Obviously, the oxidation state is 0, and iron has 26 electron. So the electronic configuration is argon 4s2 3d6. Okay. Okay, fine. So Anahita is getting trigonal bipyramidal. Fine. Ravi Kiran also trigonal bipyramidal. Fine. Okay. So 4s2 3d6. So 1, 2, 4, 5, 6, and 4s2. But since it is a strong field ligand CO, then arrangement against the Hun's rule, right? So this electron, this 2 electron will jump into the inner shell. This comes over here, this comes over here, and this also will jump here in this shell. After this rearrangement, the orbital diagram is this. Okay. 5 is the coordination number. So we required 5 vacant orbital. So one is this D, then S, and then P. So the hybridization is DSP3. DSP3 is the hybridization. Geometry, like I said, it can be TBP or it can be square bipyramidal. Which one is the correct geometry here? That depends upon the information given in the question. Now you see the square, sorry, pyramidal, not bipyramidal, square pyramidal. Okay, so if you look at the Bose geometry here, TBP is this. This is TBP. And the square pyramidal is this. In a square pyramidal, what happens? This ligand, all these ligands you see, because the bond has considerable amount of polarity. Because of this polarity, we have dipole moment, right? So because of these two dipole moment, we have a net dipole moment in this direction, net dipole moment in this direction, and these two cancels out. But because of this, we have some mu net in the molecules. Mu net should not be equals to 0 for a square pyramidal geometry. But if it is trigonal bipyramidal, this dipole moment will get cancelled by this dipole moment, and this dipole moment will get cancelled by this dipole moment, right? So mu net is 0 for TBP, trigonal bipyramidal. Since in the question it is given mu net is equals to 0, hence the geometry for this particular complex is trigonal bipyramidal. It is not a square pyramidal. Yes, correct. Understood? No doubt in this?
Yes, sir.
Right? So some information will be given. Based on that, you can find out the geometry of the molecule. Like you see, the another one, NiCN5, 3 minus we have. And in this one, it is given that it has 2 types of two type of NiCN bond length. Two type of NiCN bond length out of which 4 bond length are equal, and 1 is different. Find out hybridization, magnetic property, and geometry of the molecule. DSP3. Answer for this question, I'm writing it down. If you have any doubt, you can tell me, I will do this. The hybridization will be DSP3, and it is diamagnetic. It is diamagnetic, and the geometry is square pyramidal, because 4 bond lengths are same, so square pyramidal geometry is. Any doubt in this? Finished, all of you? Okay. Next, you see coordination number 6. Coordination number 6. The first one is, this is the most important one. We have CO, cobalt, NH3, and +3 on the complex. Hybridization and geometry for this one. It is D2sp3. NH3 is strong ligand. NH3 is strong. So cobalt +3 oxidation state, and its configuration is argon 3d6. Okay, so 3d6, the geometry is the orbital diagram is this. One, two, one, two, three, 4. And since NH3 is a strong ligand, so they will be pairing against the Hunt's rule, and it gives this one. Then these 6 orbitals will go into hybridization and forms D2sp3 hybridized orbital. Okay, geometry is octahedral, and all the electrons are paired, so it is diamagnetic. And since we have D2sp3 hybridization, so it is low spin complex. You see, low spin complex forms because of the rearrangement against the Hunt's rule. And rearrangement against the Hunt's rule is possible when the ligand is strong. That's why whenever low spin complex forms, we always have strong ligand. Okay, write down this with the hybridization, whether it is low spin or high spin, it is the nature of ligand we can identify or we can understand.
Sir, how do we determine if it's octahedral or square bipyramidal?
Both are same thing. Anyone you write, it is correct. Okay.
Sir, so in the actual molecule, will both structures exist simultaneously at the same
Both
time?
see, structure is same. Two names are there. Octahedral is same as a square bipyramidal. Same thing.
Okay, yes, sir, I'm sorry.
Okay. For a square planar, also you can say low spin, high spin, but generally we don't, assign this kind of, terms with square planar geometry. Generally with chord coordination number. But yes, if you have to pick between the two, DSP2 is the low spin complex, but SP3 we don't say whether it is low or high, right? But D2sp3 is obviously low spin complex. If you talk about sp3d and dsp3, if you have to choose, then dsp3 is the low spin complex, sp3d is the high spin complex. But mostly we talk about these two terms in coordination number 6.
Yes, sir.
Okay, so one exception we have here, right? NH3, I told you it is a strong ligand, but in some cases NH3 behaves as a weak field ligand. Only one case we have here with the metals like nickel. Okay, so this one you have to memorize because these are the exceptions. You have to keep this in mind. For example, you see, if you write down this complex, could you find out the hybridization and geometry here? NiNH3 6 2 plus. In this one, first of all, you write down one note and then you can try. One note you write down. With most of the metal, NH3 behaves as strong ligand but with some metal like nickel, it behaves as a weak filled ligand. So this is one of the drawback we can say, or exception of VBT, valence bond theory, right?
So could you repeat the last point?
Yeah. With most of the central metal ion or atom, NH3 behaves as a strong ligand, but with some metal ion, like nickel, here it is Ni2+, it behaves as a weak filled ligand. It behaves as a weak filled ligand. This is the drawback of VBT. This is the drawback of VBT. Try this one now. Hybridization, geometry, and magnetic property. sp3d2, yes, sp3d2 you are getting, octahedral complex. How many unpaired electrons are there?
2.
How many unpaired electrons? 2 unpaired electrons, that's right. So you see there is no pairing of electrons. Okay, so here in this complex, NH3 is behaving as a weak filled ligand, okay, which usually does not happen. NH3 usually a strong ligand, but here it is behaving as a weak ligand. Okay, so this example you must remember. Okay, I'll quickly write down this. Ni2+ is the charge we have, oxidation state, and its electronic configuration is nickel has 28 electron, so it is argon 4s0 3d8. Then it is 4s, and then it is 4p. Okay, so this pairing is not possible here, is not taking place, and hence this 6 orbital goes into hybridization sp3d2, and it forms sp3d2 hybridized orbital. So geometry is octahedral or square pyramidal, bipyramidal, paramagnetic with 2 unpaired electron, magnetic with 2 unpaired electron, unpaired electron. You can also think of one thing here, like if you try to understand this, if you do not memorize also, you can do this easily. See, if you think of, chalo, NH3 is a strong ligand, so pairing against the Huns tool. So what you will do, you will shift this electron pair here, right? You will have only one vacant orbital then. If you try to write down the hybridization of it, then dsp4 is not possible. Like it will be dsp3d, this kind of hybridization is not possible, right? That's why this orbital won't take part in hybridization at all, right? And hence it should not be vacant. That's why the pairing against the Huns tool is not possible. Hence it is sp3d2. Okay. And this also, they can also ask the magnetic moment of the complex. Okay. Magnetic moment. Magnetic moment is calculated by this formula, which we have also done last year in atomic structure, root under n into n plus 2 Bm, Bohr magneton, where n is the number of unpaired electron. You substitute n value 2 here, 2 into 2 plus 2, that is root under 8, and that value is 2.83 bm. Okay, so this value you must remember. Sometimes they'll give you the value of magnetic moment in the question, right? So you should know, suppose for this question, the magnetic moment is given. This complex has 2.83 magnetic moment. So first of all, what you do, you just find out the number of unpaired electron with this value. So what you need to do, you need to equate this with root under n into n plus 2, right? This should be equals to 2.83. But sometimes what happens, this becomes very complex to solve this. You know, you square and then solve the quadratic. It's difficult to do. So for that, you should memorize these values. When the magnetic moment is 2.83, the number of unpaired electron is 2. However, you can, roughly you can put some value of n and you can find out maximum 2-3 unpaired electrons will be there, not more than that in most of the cases. But what point I'm trying to make, if you memorize these values, like 2.83 is a magnetic moment when the number of unpaired electron is 2, then this helps you a lot in solving the question. So once you know this value of n, you know how many electrons you have to left, unpaired, and then you can think of the hybridization of the molecule. Similarly, if n value is 3, like this one, if mu value is, suppose the magnetic moment mu s we are getting 3.287 bm. 2.83 n value is 2, 3.287 n value is 3 we have. Unpaired electron is 3. Okay, with 3 you'll get root under 15. So root under 15, you see it is somewhere in between 3 and 4. This is what 3 and 4. This kind of observations helps you a lot in solving this kind of questions. Okay, so with nickel it behaves as weak filled ligand NH3. Okay, one last question we'll see here. Try this one. CrNH3 6 3 plus.
Sir, what is chromium configuration?
Chromium configuration, electronic configuration.
Yes, sir.
4s1 3d5. You should know it. Argon 4s1 3d5. Okay, Siddharth. Other things, magnetic property. Is it di? I think Tripan you have written ulta. Should be D2, right?
So I was getting D3 only.
Yes.
I was getting D3sp2.
D3.
Yes, sir.
How are you getting D3?
The pairing will happen, sir.
No, it's not.
Oh.
The pairing won't happen, sir.
Sorry?
So will pairing happen?
No.
Sir,
So
even though it's a strong field ligand.
This is what the two things we have discussed. No, actually here, in the question if they ask, usually they give the magnetic moment here. Mu value they'll give you. That is 3.28. This is the magnetic moment we observe. Then they'll ask you what is the hybridization and all. So
Yes.
why I'm giving this here, because you should know that this chromium also, this is not happening. And one more thing, in coordination complex, D3 you don't consider. D3, what we say, hybridization is not possible. We are not getting D3 hybridization here. But this question was actually, when they ask you, they'll give you the magnetic moment value. With this, you will have the idea that how many unpaired electrons we should have. Okay. So here also my point is, here also it is behaving as weak field ligand. So these are the few exceptions we have of VBT, drawbacks of VBT, right? So answer for this question, I'm not doing this. Answer is, it is D2sp3, low spin complex, number of unpaired electron is 3, and it is paramagnetic. How did you get diamagnetic, Aditya? Yes, correct, Srishti. Right, Anjali. Okay, fine. So these two examples you must remember, because it is not, because these are exceptions, so you must take care of this, especially that Nikhil example. This one, at least you can understand that D3 hybridization is not possible here. So we won't think of the pairing of electron. Actually, the reason is NH3 is behaving as a weak field ligand here. Okay, so these are the drawbacks of VBT. Okay, that's why, and the major drawbacks is what? That again, it could not explain the color of the complex, that what color the complex shows. This also could not explain by valence bond theory. That's why we got the new theory after this, which we call it as crystal field theory. With crystal field theory, we can find out the color of the complex. Obviously, we cannot do theoretically because we need to know the wavelength of each color, right? And then only we can say, okay, this is the wavelength we are getting, so this is the color of the complex. So color thing you have to memorize only, okay? But yes, the CFT, crystal field theory, gives us the concept that how do we understand or how do we know that what color of the complex should be? How do we calculate the lambda value there, right? That we get from the CFT, crystal field theory. So next, write down the major drawback. One note you write down after this. The major drawback for VBT is it could not explain the color of the complex. It could not explain the color of the complex. Yeah?
Yes, sir.
Sir?
Hmm.
So here it is low spin complex or high spin complex?
This one, low spin.
Previous question. Low spin only, sir.
Yes, whenever D2 you write first, D2sp3, then this S and P belongs to fourth shell, right? 4s 4p orbital is there, no?
Yes.
But this one is 3D. So lower spin complex is when the inner shell d orbital is involved in the hybridization.
Okay, sir.
Okay. High spin complex when we have S, P, D. 4s 4p 4d. High spin.
Okay, sir. Sir, and is it possible to have unpaired electrons when it's like when some pairing takes place but still unpaired electrons are remaining?
That is also possible. Like all the electrons won't get paired, See, everything depends upon the characteristics of the molecule. Like you see, the one that you did, this one, what you did, I think you did this one. In this one, you'll get 3 unpaired electron initially. And then what you did, you paired like this, right? And you said
Yes,
there's
sir.
1 unpaired electron. Yeah,
Okay, sir.
this is what you did, right? But
Yes,
this
sir, that's
you
what I did.
cannot do here, because with this, the number of unpaired electrons you are getting 1, and this does not satisfy well. But it is
Yes.
possible in some complex that there are 5 electrons, unpaired electrons. Out of 5, 2 will get paired, and accordingly will get the mu value in the complex. Possible. But those
Okay.
kind of questions, what happens? Either they'll give you mu value, then only you can find out that whether the electrons are getting paired or not. Or if 5 unpaired electrons are there, then how many electrons are getting paired, depending upon the mu value which should be given in the question. Okay?
Yes, sir.
Yeah. Next, write down crystal field theory. The crystal field theory, I'll give you a brief idea of it. Okay, because if I dictate you the theory, it takes a lot of time. So there are so many things into this. Okay. Actually, what happens, first of all, in this theory, there is one assumption. And what is the assumption? Assumption is that the ligands and the metal ion we consider as a point charge. Okay. So assumption is what? Ligand and metal ion are considered as point charge. Okay. Now it is point charge, so there will be what? There will be this thing, electrostatic attraction. Ligand is negatively charged. Metal ion is positively charged. So we'll have electrostatic attraction between them. So the entire theory is based upon this particular assumption, that ligand and metal will have electrostatic attraction. But now what happens? We have metals and d orbitals of metals are there, right? And ligands are trying to approach the metal, right, with its lone pair of electron. And there are electrons present in d orbitals of the metal already, right? So when these ligands approach the metal ion, then suppose we have certain electrons present in some of the orbitals of metals like this, some arrangement we have like this. Randomly I have drawn this, okay? So when this ligand tries to donate the electron pair, right, so these electrons repels the coming electron from the ligand. Okay, repels in the sense what? The orbital which consists, which has electron present into this, the d orbitals of the metal in which the electrons are present, those orbitals and the coming electron, we have repulsion between the two. So it is possible that some of the orbital has 1 electron, 2 electron, or some of the orbitals are vacant also, right? So obviously the orbitals which has electron, they experience more repulsion, and the orbitals which has no electron, they experience less repulsion, right? So what we can conclude from this, that when this ligand tries to donate the electrons into the orbital of the metal, right, there will be uneven repulsion between the orbital and the electrons that comes from the metal, that comes from the ligand, right? Because of this uneven repulsion means some of the orbitals experience very high repulsion and some of the orbitals experience less repulsion, right? Because of the presence or absence of electron. So because of this uneven repulsion, this orbital splits into 2 sets of orbital. Mainly 2 sets, depending upon the geometry, we can have different number of orbitals, right? It splits into 2 sets of orbitals, which we call it as splitting of orbital. And this splitting, we call it as crystal field splitting, right? In this splitting, what happens? Some of the orbital goes on to the higher energy level and some of the orbital comes down to the lower energy level by maintaining, by maintaining the average energy of the complex. Average energy will be maintained. This will increase energy, some positive value of delta O, and some negative value of delta O. So that average energy will be maintained. Like this, the splitting takes place. Okay, so this is what actually happens in the coordination complex. Okay, and this is crystal field theory. So to sum up all this, wait, just a second. To sum up all this, what we can say that crystal field theory is based upon the electrostatic attraction between the ligand and the metal ion. Why electrostatic attraction? Because we are that the ligand and the metal ion are the point charge. Okay, so when the electrons from the ligands approach the d orbital, right? So because of the electron already present in the d orbital, will have uneven repulsion in the d orbital, and hence the d orbital, to minimize the repulsion, it splits into two parts, okay, or two sets of orbital, or more than two also possible, depending upon the geometry. It splits into two parts. This splitting, we call it as crystal field splitting. In this splitting, some of the orbitals goes on to the higher energy level, some of the orbitals goes down to the lower energy level in order to maintain the average energy of the orbital. This is crystal field splitting. Did you understand the basics of it?
Yes.
Got it? So all these things are given in NCERT properly. They have written in NCERT. I would request all of you, after the class, at least 10-15 minutes you give to go through the entire theory of crystal field theory. Because if I dictate, it will take a lot of time. Okay, so I'm not dictating this theory, whatever I said now. So I want you to go through once. Okay, I'm not dictating all these things. So the thing is, next, when this orbital splits, right? This orbital splits into groups actually when we have octahedral complex, because this kind of splitting we observe in different geometry. So we'll have a splitting in octahedral complex, we'll have a splitting in square pyramidal complex, we'll have a splitting in tetrahedral complex, right? All these three splitting we'll see, right? Understood? So first of all, you write down just basics, you write down here. According to this theory, the bonding in the coordination complex is completely electrostatic. Again, I am repeating. According to this theory, the bonding in the coordination complex is completely electrostatic, and we assume the ligand and the metal ion as a point charge. Point charge. Okay. The complex. Sorry.
Can you repeat, sir?
And we assume the second line or the first line from the beginning. I'll repeat from the beginning. Wait. According to this theory, the bonding in the complex is completely electrostatic. In which the ligand and the metal ion are considered as point charge. In which the ligand and the metal ion are considered as point charge. Next line, the complex is regarded as the combination of CMA, that is central metal atom, the complex is regarded as the combination of CMA surrounded by the ligands. Okay, so in the entire theory, I'm cutting short to it because it takes a lot of time. Again, I'm telling you this. Just one line after this you add. Because of the interaction between the ligands and the metal ion, because of the interaction between the ligands and the metal ions, the d orbital experience uneven repulsion. The d orbital experience uneven repulsion, and it splits into and it splits into two sets of different orbitals having different energy. And it splits into two sets of different orbital having different energy. So these sets that we get, the splitting of orbital, it happens in this way that all non-axial orbital, for example, dxy, dyz, dzx, all these non-axial orbital, it goes into one set, okay? And this set we call it as T2G orbitals. T2G orbitals, these are non-axial orbitals. Axial orbitals are called EG orbitals, for example, dx square y square and dz square. These are axial orbitals, right? This T2G and EG, you don't have to think about it. These are spectroscopic terms. We call it as spectroscopic terms, right? Just a group of orbitals, it's said to be this and this. Not required this, but when we distribute orbitals, then this grouping, this terms helps us to understand the distribution of electron. That's why we have given this term, right? Not much important. Fine. So this splitting of orbitals, right? There are certain factors which affects the splitting of orbitals. Okay, like we have the position of transition metal, oxidation state, and other things, right? There are various factors which affects the splitting of orbitals. So how splitting takes place in different complex, whether it is octahedral, square pen, or tetrahedral, that we'll discuss a bit later. First, we'll see that what are the factors which affects the splitting of orbitals, right? Write down the magnitude. Next line, the magnitude of splitting depends on the following factor. Depends on the following factors. These factors are not important. Only two things you have to keep in mind here. Otherwise, it is not at all important. Okay, the first one here, the first point is a bit important, and the last one. Okay, just you need to know the the basic result of it. Write down the position of the first factor is position of transition metal in the periodic table. In the periodic table. Write down. The magnitude of splitting increases as we go down the group. The magnitude of splitting increases as we go down the group. For example, if you compare the splitting in PTCl4, 2 minus and PDCl4, 2 minus, okay. As we go down the group, the magnitude of splitting increases. So platinum produces more splitting than palladium, okay. The second factor we have, oxidation state of metal. Oxidation state of metal. As oxidation state of CMA, central metal atom, increases, splitting increases. Because more positive charge, more will be the attraction, and hence more will be the repulsion in the d orbital, more will be the splitting. Okay, so easily you can compare this FeCN6 3 minus and FeCN6 4 minus. Obviously, in the first one, the repulsion will be more. Okay, one more, in fact, two more we have. If the charge on the central metal atom increases, splitting increases. Oh, just a second. It's the same thing. No? Charge on the central metal. Oh, it's just. Wait. If the charge on the central metal atom is same, if it is same, then the metal with higher number of d electrons, will have lesser splitting. So if you consider this CO2 plus, suppose you have a complex in which you have CO2 plus oxidation state and Ni2 plus oxidation state. So in CO2 plus, the splitting would be more, because if you look at the configuration of this, it is argon 3d7, and for nickel, it is argon 3d8. So more electrons, lesser will be the repulsion. The most important one is the nature of ligands. Okay, this is what I was talking about. Strong ligands produce more repulsion and weak ligands produce lesser repulsion. The magnitude of repulsion actually gives us the idea about the nature of ligands. So write down into this. The ligands which affects only a small degree of crystal field splitting are called weak field ligands. Okay, the ligands which affects only a small degree of crystal field splitting are called weak field ligands, and those which affect a large splitting are called strong field ligand. Okay, and those which affects a large splitting are called strong field ligand. Next line. When these ligands are when these ligands are arranged in order of the magnitude of their crystal field splitting, will get a series which is called a spectrochemical series. Will get a series which is called a spectrochemical series. Just a second. Okay, so a spectrochemical series we write down. Just a second. Okay, this is spectrochemical series. From I minus to ETOH, these are weak field ligand or weak ligand simply. These are moderate, and all these from NH3 to this, these are a strong ligand in general. Strong ligand. Actually, water, if you see water is present in between, whatever ligand is present out right side of water, ligands are considered as strong ligands in general, and including water, whatever ligand is present left to the water molecule, these are weak ligands. So whether the ligand is weak or strong, that idea we get from the splitting in the orbital, right? Crystal field splitting. Copy this down. Done? Okay. So this is the spectrochemical series and the nature of the ligand, weak or strong. Okay. So if the two complexes given and the ligands are different, then depending upon the nature of the ligand, weak, strong, or moderate, you can easily compare the splitting in the complex. Okay. Now you write down crystal field splitting in octahedral complex. Three complex we have to discuss: octahedral complex, square, planar, and tetrahedral. So octahedral complex we'll discuss in detail. Everything is same only in other two complex. So we'll just see in the other two complex, we'll just see the splitting of orbitals, how the orbitals splits. Okay. So we need to first of all, we need to first of all identify that which two orbitals will have the maximum repulsion. Like which two orbitals will have the maximum repulsion. Because the complex is octahedral, so one ligand comes from the top, another one comes from the bottom. This is the third one, then fourth one, fifth, and then sixth. right? So in all these directions, the ligand approach the metal. Metal is present here in the center. All these are ligands. 1, 2, 3, 4, 5, and 6. So we can easily consider the axis along these lines along these lines we can consider the axis because the angle is 90 degree. And one like x, y, and z axis. So obviously along this line we have dx square y square orbital, right? Dx square y square orbital present along this line. Right? And along this line we have dz square orbital. So the two orbital set of orbital we have T2G and EG. T2G is all non-axial orbital, dxy, dyz, and dzx. And T2G EZ has two orbitals, which is dx square y square and dz square orbital. So when this ligand approaches the metal to form an octahedral complex, okay, so EG orbital will have the more repulsion, and this will go to the higher energy level, and T2G will come down to the lower energy level by maintaining the average energy of the complex. Okay, so how the splitting takes place? I'll show you the diagram for that. You have to draw this. Just a second. This one you see. This is for tetrahedral complex, sorry, octahedral complex. Okay. See this, what happens here. This y-axis is the energy, and this x-axis is the distance decreases between the metal and ligand. Like if you're going left to right here, means ligands are coming closer to the metal. Okay, so this x-axis you write down, distance decreases between the metal and ligands. So as the distance decreases, you see the repulsion starts increasing because the ligands are approaching the metal. The energy of this orbital starts increasing, it goes to the value here. This is step 1, energy goes to this value. Then further the electrons, the ligands comes closer, and the orbital splits into two parts. One is this, other one is this. You see this one? This one is EG and this one is T2G. By maintaining the average energy, right? This let it be very center and all, it's not required. Simply average energy level is here. Now this value is 0.6 delta O. It's not 0 or not. It is O. O stands for octahedral. Okay. It's basically the unit of energy in this complex, octahedral. Okay, this equals to a fixed value of energy for a given complex. This value will be different for different complex. Okay, those energy we don't have to calculate, right? It's not required. 0.6 delta O. below it is minus 0.4 delta O, right? Total energy is delta O. That's how the splitting takes place. Copy down this first.
Sir, why is it minus 0.4 delta O?
Because the energy is decreasing from that point. So minus just represent the energy decreases. It's just a sign convention, you can say.
Yes.
Sir, can we say that the energy of the d orbitals in step 1 raises up to 0.2 delta naught or delta O?
0.2 delta O. No, it's not 0.2. Sum is this plus this is delta O only. Plus minus sign is just represent the energy is increasing for this and decreasing for this. That is this. Total sum is delta O only.
Okay, yes sir, yes sir.
Right. Nothing in step 1. As the ligands are coming closer to the metal, slowly the energy of d orbital is increasing and it reaches to the maximum value and then it splits into the two parts.
Step 1 is the excited state.
Excited state, we cannot say excited state because in that excited state generally when electron jumps into the higher energy level. Here the transition of electron is not there, but because of the interaction of the electron between d orbital and the ligand, overall the energy of d orbital is increasing, goes to a maximum value before splitting.
Okay.
Sir, and the way we have assumed the ligands are approaching the metal atom like along the axis, is it only an assumption or is it actually like that?
No. Actually, we are assuming octahedral complex. No. To form an octahedral complex, obviously ligand has to approach this way. Otherwise, it won't form.
Yes, sir.
And it
But
is
then,
just there to tell me.
sir, but then the axis can be like oriented in any other way also, right?
Or other
Or it
complex.
has to be this way.
See, just a second. Actually, this way I have, we explain things this way so that you can memorize it, you can understand it. But actually what happens when suppose the ligands are approaching from, from the other side, from the every side of towards the metal, then obviously the ligand also repel each other. There will be some crowding and then some lone pair the ligands are coming. So lone pair will also repel each other. Then the ligands will arrange themselves in such a way so that the repulsion will be minimum. And then actually
Yes, sir.
the geometry of the complex we get, right? We
Yes,
are
sir.
understanding this in a different way. What I'm telling you, that to form an octahedral complex, the ligand has to approach this way so that you can understand this, that these orbitals are involved and why. See, if I tell you this thing, no, that ligands approach the metal to minimize the crowding and repulsion of the electron pair, it will arrange this way and forms the octahedral complex. Like that also I can explain. But then when I tell you that this orbital, these two orbitals goes to the higher energy level, then you will ask me, sir, why these two orbitals goes to the higher energy level? To clear this thing,
Yes, sir.
we are understanding it this way, because if octahedral complex is forming, the ligand has to approach along these lines, and along these lines we have these two orbitals present. That's why in these two orbitals we have maximum repulsion. So we are trying to understand this in a different way, but the actual thing is ligands are randomly approaching the metal, and whatever the arrangement of ligands in the space which provides the minimum energy to the complex and maximum stability, that will be the geometry of the complex.
Okay, sir. Yes, sir.
Got it? Yeah. All of you drawn this?
Yes, sir.
Okay. So this is the splitting of orbitals. Now you see, if you want to distribute the electron into this one, from which orbital you have to start the distribution of electron?
From the lower energy?
From the lower energy orbital, yes, that's right. Because in atomic orbital, we also did the same thing. Lower energy orbital gets filled first, right, by n plus L rule. So here also, if you want to distribute the electron in this, because this is the actual case we have, right? Now, if you want to distribute the electron, this 3 orbital will get filled first, and then the electron goes into EG orbital. So first T2G and EG, that's one thing, okay? Very, very carefully listen to me. Now, whether this distribution of electron follows Hund's rule or not, that depends upon the nature of the ligand. If the ligand is strong, then this splitting will be high. That difference of energy will be more between the two orbitals. And if the difference of energy is more, then the distribution of electron does not follow Hund's rule. Right? We'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. If the ligand is strong, energy gap is high. If energy gap is less, then the distribution of electron follows Hund's rule. In that case, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. Okay. So this is the distribution of electron. First thing is that, right? How do we find out the crystal field splitting energy? Because obviously the two sets of orbital will have an energy difference between the two sets of orbital. So this energy difference also we can calculate by a formula, and that formula is called CFSE, crystal field splitting energy, and it is given by minus 0.4 times X plus 0.6 times Y delta O. Again, it is O, it is not naught. Okay, delta O. O stands for octahedral. X, what is X? X is the number of electrons. Number of electrons. 0.4 is associated with which orbital? 0.4 is associated with T2G orbital, right? T2G. 0.6 is associated with EG orbital. You see this, X is the number of electrons present in, T2G orbitals. Y is the number of electrons in EG orbitals. Okay, so distribution of electron, if you know the XY value, that XY value you can substitute here and you can find out CFSE in terms of delta O. Is it clear?
So,
yeah.
So we always have 0.6 delta O and minus 0.4 delta O, right, for when it splits?
I didn't get you. Come again.
So like we'll always have 0.6 delta O for EG and minus 0.4
Yes,
for
on
T2G, right?
even for square planar also it's the same thing. This is the splitting, and all these are experimental. How the orbital splits.
So but then how do we determine whether the splitting is large or less, even though the fraction is the same?
See, when the for different this delta O value, it depends upon the complex. It is not fixed for all the complexes. Okay.
Okay, sir.
I'll give you one example if you want. This delta O, I'll come to this. Okay, just give me some time. I'll come to this. Otherwise, everything will mess up.
Okay, sir.
So you see here, I was talking about this CFSE. So once you know the number of electrons in the two orbitals, you have the value of X and Y, and then you can find out CFSE in terms of delta O. Delta O for a given complex will have a fixed value. It's not like this value is universal like gravitational constant, right? Delta O will differ for different complex. It has different value for different complex. Okay, it's not constant for all the complex. Okay,
Yes,
but
sir.
since we do not calculate those values, okay, even you don't have to calculate CFSE normally. Hardly you have to calculate this. That is not required. Even they ask you also this in the option also they'll give delta O only. You just need to know this X and Y. That is it. Okay, but for your understanding, I'll discuss one example of this. Okay, so the point is how to distribute the electrons. Like I said, the distribution of electrons depends upon whether the ligand is strong or not. Okay, so in case of a strong ligand, the gap of the energy between the two orbitals, Eg and T2G, will be more, and in that case, we do not follow Hund's rule when the ligand is strong. When the ligand is weak, we'll follow Hund's rule and we'll distribute the electron as we do in atomic orbital. Okay, so heading you write down here, distribution of electron. First one, in case of weak ligand, write down simply, in case of weak ligand, we'll follow Hund's rule. So the distribution will be according to Hund's rule. So first the electron will go into T2G because it has the lower energy. Then the electron will go into Eg because we are following Hund's rule. Then again electron will go into T2G. And again the electron will go into Eg. Right? So first 3 electron will go into T2G orbital. 4th and 5th electron goes into Eg orbital. 6th, 7th and 8th electron goes into T2G orbital. 9th and 10th electron goes into Eg orbital. Right? So suppose the ligand is weak and we have D5 configuration. Suppose you need to find out CFSE for D5 configuration, right? So D5 configuration is still here. What is the X value? Could you tell me? What is the X value? 3. X value is 3. Y value is 2, right?
Yes, sir.
So this X and Y value you substitute here. 3. Y value is 2. You substitute it here. You'll find out CFSE with this formula, and that is minus 0.4 times 3 plus 0.6 times 2 delta O, and this is equals to 0 crystal field splitting energy. Is it 0? Yes. Right? CFSE is 0 for this one. Similarly, for any configuration you can find out depending upon the ligand, the nature of the ligand. Suppose this D8 configuration we have. Then the number of the value of x is what? The value of x is 6 and y is 2. Substitutes x and y here, you'll get CFSE in terms of delta O. Did you get this, all of you?
Yes, sir.
Okay.
Yes.
Yeah, fine. Now, when the ligand is strong, second case, in case of a strong ligand, the energy gap between the two orbitals, Eg and T2g, will be more, and it does not follow, distribution of electron does not follow Hund's rule. And hence, the distribution of electron will be like this. We have T2g, and then the electron will go into Eg. So first 6 electrons will go into T2g orbital. 1, 2, 3, 4, 5, 6. Then 7, 8, 9, 10. Okay. So CFSE is equals to, suppose we have an example, CFSE for D8 configuration. So for this case, X value is 6 and Y value is 2. CFSE is equals to minus 0.4 times 6 plus 0.6 times 2 delta O. So it is minus 1.2 times delta O is the energy here. One more thing we have here that we call it as average pairing energy. Okay, note you write down this. All these small informations, they have asked question on this. That's why I told you in the beginning that in this chapter, you'll get many different kinds of questions. Okay, that is possible, they can frame. All these small informations are important, right? Like you see, average pairing energy. Because of this only, the electron does not follow Hund's rule over there. Average pairing energy. It is represented by P, capital P. Write down. It is the energy required for the pairing of electrons in the same orbital. It is the energy required for the pairing of electrons in the same orbital. Okay. So in case of weak ligand, what happens? The delta O, the energy gap that you have between the T2g and Eg orbital is lesser than the pairing energy. And that's why pairing takes place over there, right? And follows Hund's rule. But when the ligand is strong, when the ligand is strong, the relation is this. Delta O is greater than P, average pairing energy. And that's why it does not follow Hund's rule. Okay. This relation also they have asked many times in the exam.
So could you explain this again?
Sorry?
Could you explain this one again?
This one, nothing, it's just a definition. See, when you want to pair up an electron in the same orbital, some energy must be required because the electron has to, to be filled into that particular orbital. That energy, we call it as average pairing energy for the pairing of electrons. So when this gap, the T2g and Eg orbital, if this gap is lesser than this case, lesser than the average pairing energy, then the pairing takes place and it follows Hund's rule if this gap is lesser than this energy. But when the gap is more, then the pairing energy is lesser than the gap of the two energies orbital, like P2G and EG. So in that case, the pairing of electron is difficult. That's why the distribution of electron does not follow Hooke's rule.
So, but if more pairing energy is required, then okay, 1 second.
No, more pairing energy is not required. Average pairing energy is fixed for the complex. Now, depending upon the ligand, we can have different delta O, the gap of the two orbitals. If that gap is less than the pairing energy, then pairing takes place. If that gap is more, then the pairing won't take place.
Okay, sir.
No, average energy level is the energy of the orbital. Average energy of all the orbitals. Pairing energy is for electrons in the same orbital. Now, one more thing you see, the drawback in the previous one is mainly the color we cannot find out for the complex. Now you see this calculation is difficult and they won't ask you to calculate the one that I'm going to talk right now. You see, if you want to find out the energy of the color of the complex, then this is because suppose here is the electron, right? Here the electron, one orbital, one electron is there, two electron is there, three electron is there. It is present into this orbital. Then what you do, you just provide some energy with the help of light on this complex, right? Electrons takes up this energy and converts and jumps to the higher energy level. Provides energy so that this transition takes place, right? So this energy we can find out by CFSE, right? And this energy is equals to what? You can write delta E is equals to Hc by lambda. Per mole if you do, then Na you have to multiply here, divide here. This energy gap is nothing but CFSE, and that is nothing but CFSE is equals to Na times Hc by lambda. All these values, you can find out the wavelength, like which is getting absorbed in this process. And that wavelength corresponds to one particular color. That will be the color of this. The complementary of that color will be the color reflected by the complex. So with this method, we can find out the color of the complex. So that drawback has been resolved. But for us, we cannot find out these values, right? Suppose suppose any means you can find out lambda. But how do you memorize that this lambda corresponds to this particular color? Are you getting my point? You cannot memorize wavelength for all the colors, no. That's why they generally do not ask this question in the exam. Sometimes they have asked, in that case you cannot do anything, but you have to know that this ion in this oxidation state will show this color, that you have to memorize. But how to find out the color of the complex method is this. Did you understand it?
So the energy difference is the CFSE.
Yes.
So then what is delta naught?
CFSE.
Delta O, sorry.
Delta O is that only. See, if I write down CFSE, so in terms of delta O, the total is delta O only. No, it is split into this. So 0.6 plus 0.4 is delta O only. So delta O is this gap, and this is equals to, like, this is a unit. It's see, I'll take one example. Just a second. Suppose I have a complex. This you will understand. Just a second. For this complex, usually this kind of example is not given in most of the book, but I have taken one example for this. TiH2O6 3+. This is the complex we have. For this, if you find out delta O, that would be equals to the energy E per mole calculation is there. So this would be equals to Na times Hc by lambda. So what wavelength it absorbs, that we know by the experiment, right? So when you substitute all the value, I'm giving you this, this fact here. Na value, 6.022 into 10 to the power 23. H value you know 6.6 into 10 to the power minus 34 joule second. 3 into 10 to the power 8 meter per second. This divided by the wavelength that this complex absorbs is 20,300 into 10 to the power 2 meter inverse. The value is, and this is the experimental value. Okay, when you solve this, you'll get delta O equals to 241.97 into 103 joule per mole, which is approximately 242 kilojoule per mole. So you see this, for this complex, this delta O is nothing but the value of energy, which is this. And that gap is nothing but here. And that is what I am talking about here, you see. This gap is the energy, right? This energy is delta O, right? That is the splitting thing we have, delta O, which is equals to Hc Na times Hc by lambda, because per mole calculation we are doing. Did you understand it?
So, but CFSE is not delta O, right? So CFSE is not delta O, right?
CFSE is the energy associated with the distribution of electron, because X and Y values. Oh, at that time I said CFSE. No, it's not. It's delta O actually. The energy gap is delta O. CFSE is the energy associated with when you distribute electron in different orbitals. In that case, there will be some exchange in energy. That is CFSE.
Okay, sir.
What does that
Understood?
signify, that exchange energy and all?
Which one?
So that's CFSE.
CFSE, you see, CFSE formula is what? Minus 0.4 times X plus 0.6 Y is equals into delta O, right? X and Y is what? X and Y is the number of electrons. So with different value of X and Y, you'll get different value of CFSE. Correct?
Okay.
So this CFSE is what? CFSE is because you are distributing the electron, and when the electron goes from one orbital to another orbital, or you put one electron into one orbital, there will be some exchange in energy, right? That energy signifies by CFSE.
Okay, sir.
Because X and Y are the number of electrons, right? So if X and Y changes, CFSE also changes. That is associated with the number of electrons present in the orbit.
Yes, sir.
Okay, so this thing delta O is, you can say it is a kind of unit for each complex. Okay, delta O I have given you for one. Okay, but it will be different for the other, complex. But you don't have to calculate this. They won't ask you. I have never seen any question in which they ask you to calculate delta O. If they ask, they'll ask you to calculate in terms of delta O. So you don't have to worry about it. But yes, to understand the concept, you should know this. That like this, we can find out energy, wavelength, and then delta O. Corresponding to that, the complementary color is the color of the complex. Clear? Understood?
Yes.
Fine. We'll take a break now. After the break, this is actually the major thing we have done. Only two things we have to discuss, and this much, the distribution of electron and everything, we don't have to discuss for square, planar, and tetrahedral. Just we need to see how the orbitals splits in these complexes, square, planar, and tetrahedral. Which orbitals goes onto the higher energy level, and which orbitals comes down to the lower energy level. That only we need to see. That is a diagram we need to understand first. Nothing much, like this distribution of electron and all. This has the same concept. We don't have to do that. They won't ask also. Understood?
Yes.
Yeah. Okay. Fine. Take a break now. We'll resume the session at 6 or 7:10. Okay, 20 minutes. 7:10 will resume. Take a break, guys.